So far, we have gone through the various semiconductor devices like diode, its applications, BJT, and FET. Now, let us have a look at another semiconductor device. Of course, it's an integrated circuit known as operational amplifier. Okay, amplifier. Okay, basically, it is a high gain voltage amplifier whose gain is around 10 power 5 to 10 power 8. You can imagine how much large it is when compared to BJT or FET. Their gains are in the order of tens to hundreds. Okay, whereas the gain of operational amplifier is extremely high and it is an integrated circuit. So far we have studied discrete components. Now first time we are looking at that integrated circuit IC, I can say. And most commonly used integrated circuit is IC741 LM series IC741, which looks like this, and this is the pin configuration of IC741. It is an 8-pin integrated circuit and requires two power supplies. One is a positive power supply VCC, another is a negative power supply. It has two input terminals. One is inverting input terminal, which is denoted by the voltage at the inverting terminal is denoted by V minus, and another is non-inverting input terminal, and the voltage at the non-inverting terminal is denoted by V plus. Pin number 8 has no connection. Okay, and it doesn't contain any ground terminal. And two more terminals known as 1 and 5, they are known as offset null. What is meant by offset? We'll see. Nothing to worry. Next, what about the symbol? The symbol of the operational amplifier is like this. The inverting terminal is denoted with negative symbol and the voltage here is V minus as I told, and the non-inverting terminal is denoted by V plus. Okay, positive sign, and the voltage here is V plus. And the pin number 6 is output. Pin number 7, this is pin number 7, right, VCC, and pin number 4, here I wrote it, of course it is pin number 4 minus VEE. Pins 1 and 5 are offset null. Okay. And here the output of operational amplifier is related to the two inputs by means of the equation V output is equal to A into V plus minus V minus, or the voltage V plus minus V minus, it is also denoted by VD, means the differential input. The difference of voltages between non-inverting and inverting terminals is denoted by VD. Okay, the output is related to the two inputs by means of this equation. Okay, next, suppose no input is given either at inverting terminal or at non-inverting terminal. According to this equation, the output should be 0. But sometimes due to the presence of the power supplies VCC and VEE, there is a scope for a non-zero DC present at the output, which is known as output offset voltage. Offset means unwanted output. Expected is 0 when 0 input is present, 0 input is there. Then, but if you get a non-zero output even with 0 input, that is called as offset. To nullify that offset voltage, we make use of the pins 1 and 5, which are known as offset null, to nullify the offset. How it is so, all those things, because it's a very first session. All right, you will, down the line you will be learning all those things. And if you look at the internal architecture of this integrated circuit, it has 20 transistors inside this. It's right, 20 BJTs starting from Q1. See, Q1 to Q20, the last one, and 11 resistors. Right, and if you look at this, see, current mirror circuit, and here one more current mirror circuit, active current mirror load, and Whittler's current mirror circuit, Darlington common emitter amplifier, and push-pull emitter follower. You know all these names which we studied in BJT and FET. Okay, so integrating all those things, all those circuits, and designing this particular device, which is which is providing a very high gain, ranging from 10 power 5 to 10 power 8. Of course, this IC741, this integrated circuit provides a gain of 2 into 10 power 5. Okay. General range is 10 power 5 to 10 power 8. That depends upon the model of the IC we are using. But as far as this particular IC is concerned, the gain provided is 2 into 10 power 5. Okay. So we will discuss all these things. At this stage, you need not worry about it. It has two power supplies. Why the name VCC means the supply is positive supply is connected to the collectors of all the NPN transistors or the emitters of PNP. If it is positive supply is connected to the collectors, no, we are well aware. Okay. So, or we give a negative supply to the emitter. Okay, see, these are the emitters. And of course, here the current mirrors are made of PNP transistors. PNP emitters are connected to the positive supply. See this. These are connected to positive supply. Or you can use NPN transistor with collector. Nothing to worry. And here the NPN transistors with whose emitters are connected to the negative supply. This emitter, the emitters and all. Okay. Like this. It is PNP transistor whose collector is connected to the negative supply for proper biasing to see that the transistor is operating in the active region. Okay. So this is the notation we follow. And if you look at the points what I mentioned so far, the operational amplifier is a voltage amplifier with extremely high gain. Extremely high gain. For example, the popular IC741 op-amp has a typical gain of 2 lakhs volt per volt. Anyway, gain has no units, voltage by voltage. Also expressed as 200 volts by millivolts. The fact that what makes this operational amplifier distinguishable from all other voltage amplifiers is the gain it provides. Yes, due to this high gain only, it is distinguishable compared to BJT or FET. And we have inputs as minus and positive symbols, which are designated as inverting and non-inverting terminals respectively. The terminal with negative sign is inverting terminal, and the terminal with positive sign is known as non-inverting terminal. Okay, and their voltages with respect to the ground are denoted by the V minus and V plus symbols. Okay, that is the notation I follow throughout. Op-amps do not have a 0 volts or ground terminal, as I mentioned, and it needs a dual power supply. Absolutely, it requires two power supplies, one positive and one negative supply, and ground reference is established externally by the power supply common. Yes, once you are using power supply means positive terminal is going to the circuit, and the negative terminal can be used as the common point. The same way, or if you want to use negative power supply, negative terminal goes to the circuit and positive terminal will be used as a common terminal. That's it. That is only the common point. But op-amp does not have a specific ground terminal. Okay, and the power supply voltages are usually denoted by VCC and VEE, and the typical values of these voltages, what is the range of the power supply, means 5 volts minus 5 volts like that, and 10 minus 10, 12 minus 12, 15 minus 15, 24 minus 24 like that. These are the ranges you can see as far as the power supplies of the operational amplifier are concerned. Okay. Then what about the significance of the input terminal? I mentioned inverting and non-inverting terminals. Why the name inverting or non-inverting? See this. I'm just taking this operational amplifier circuit. Here I am applying some signal Vm sin omega t. It has two power supplies, VCC and minus VEE, V output. Then what is the output? It is A into V plus minus V minus, in which V plus is 0. So it is equal to A into 0 minus Vm sin omega t. it is equal to minus A into Vm sine omega t. Okay. Then if you draw the waveform, the negative sign, if you observe, what is the meaning of the negative sign? The output is 180 degrees out of phase with the input. Means if the input is positive, the corresponding output should be negative. And input is negative, the corresponding output is positive. This way we can see. So output is amplified version of the input, but it is inverted. Right? Means if you apply any input at this particular terminal, output will be inverted form of the input. That's why the name inverting input terminal. It is denoted with negative sign. Okay, so the negative sign is coming here. That is the notation we follow. Okay, similarly, the non-inverting input. So exactly opposite action. Minus plus, it is connected to ground. It is Vm sine omega t. What is the output? A into V plus minus V minus A into, directly I am writing Vm sine omega t. So there is no negative sign here. Means output is amplified version of the input. And input is positive, corresponding output is positive. Input is negative, corresponding output is also negative. So there is no inversion at all. Hence the name non-inverting input. Earlier one is performing inversion. This is not performing any inversion. No inversion means not non-inverting input terminal. So this terminal is denoted with positive sign. Non-inverting input. Okay, that is the idea here. Inverting and non-inverting terminal. Why the name? Means this is the reason. Okay. Next, what is the equivalent circuit of operational amplifier? Okay, we have seen that the op-amp symbol is like this. Diode symbol, BJT, FET, all the symbols, right? We know the similar way op-amp symbol is like this. And we have gone through why the names inverting and non-inverting terminals. The next point is equivalent circuit, diode equivalent circuit, BJT, FET, all those equivalent circuits we know. Now coming to the equivalent circuit of op-amp. Basically, it is a voltage amplifier, and hence the equivalent circuit of a voltage amplifier is considered for op-amp as well. What is the equivalent circuit of op-amp means? Just same as the equivalent circuit of a voltage amplifier. Okay, so if you look at the voltage amplifier, okay, here I am just writing. If you take a voltage amplifier, what is the equivalent circuit, friends? Input side it is Ri and output side A into Vi. A dependent voltage source in series with a resistance. It is input and output. We are well aware of this one. Okay. So what about the Ri value and RO value? Ri should be extremely high, we studied, and RO should be extremely low, and gain should be extremely high. These are the requirements of a voltage amplifier. Okay. So with BJT or FET, you may or may not get all these things according to the required. We may not get these values while thinking of designing a voltage amplifier using them. Whereas op-amp is an integrated circuit which is meant or which is designed in such a way that it provides high input impedance, low output impedance, and high voltage gain. First of all, coming to its equivalent circuit, yes, input side a resistance Ri and output side a voltage dependent voltage source value A into Vd in series with a resistance Ro. Okay, and in the two terminals, one terminal is V inverting terminal, another is non-inverting terminal. Voltages are denoted by V minus and V plus, and output output is equal to A into Vd, which is equal to A into V plus minus V minus. Vd is the potential difference between voltages at non-inverting and inverting terminals. Okay, so the equivalent circuit includes a differential input resistance Ri. It is known as the differential input resistance, a voltage gain A, and the output resistance Ro. These are the three parameters, and these are the open loop parameters. See, we are considering this circuit without applying any feedback. It's an open loop system, and these are open loop parameters. Also, V output is equal to A into Vd, where Vd is equal to V plus minus V minus. It is also known as differential amplifier or difference amplifier, as the op-amp responds to the difference between its input voltages. From this equation, we can understand that op-amp is amplifying the difference of the two input voltages. Hence the name differential amplifier or the difference amplifier. Okay, and it's not their individual values, it is always responding to the difference of the two inputs. Is it not so? It's not like I'm not writing like A into V plus or A into V minus. What is the exact equation? This. Okay, and what about these values? Input resistance is in the order of mega ohms. See, the parameters of op amp, typical range, the open loop gain, as I mentioned, 10 power 5 to 10 power 8. If you take an ideal device, practically it is very large. Ideal value I can write infinite. And input resistance Ri, it is 10 power 5 to 10 power 13 ohms. You can imagine how much large it is. Extremely high. And 1 mega, 2 mega itself, we treat it as open circuit in analog. If that is the case, 10 power 13 means very much comfortably I can treat it like infinite ohms. Open circuit. Ri is infinite. And output resistance RO, typically its value is 10 to 100 ohms. And ideally it is 0, means short circuit. Power supply range, it is mentioned earlier also, 5 to 24 volts is the range. So, if that is the case, see, if you look at the values of ideal op-amp, what we can write, input impedance is infinite means I can treat it like open circuit, and output resistance is 0 means short circuit only, no RO is shown. Anyway, A into Vd, that remains as it is. We can write it the same way, A into Vd, A into V plus minus V minus. This equation does not change. The only thing is it is infinite, open circuit at input side, short circuit at output side. We can write like this. Then here I am mentioning gain is around 10 power to 10 power 8. If that is the case, what is the value of the output? What is the possible value? Suppose my power supplies are VCC is equal to some 15 volts and VEE, or right, I can write VCC is equal to VEE also, doesn't matter, and minus VEE is equal to minus 15 volts, means here I am applying some plus 15 and here it is minus 15 volts. Then the maximum value of the output, V output, whatever may be the gain, okay, then whatever may be the gain, V output maximum, it is equal to VCC 15 volts, I can say, ideally VE, right, ideally I can say VCC, that is 15 volts, this is the ideal value. Practically speaking, less than the power supply by 1 volt, okay, and output minimum, is equal to minus VEE, that is minus 15 volts. That is also ideal value. Practically speaking, but practically output maximum is equal to VCC minus 1, that is 14 volts, and output minimum is equal to minus VCC plus 1, that is minus 14. These are the practical values. Whatever may be the gain, game looks like 10 power 5, 10 power 8, etc. Let it be, but the output never exceeds the power supplies. Okay, throughout I follow a notation that output maximum is equal to VCC and output minimum is equal to minus VW. Okay, that never, what that is against, see, as the gain is infinite, is it possible to see infinite output? Meaningless. You will never get a infinite output from finite input. Okay, output limits are set by the power supplies. The power supplies will decide the output limits. And if you get infinite output as the gain is infinite, which is against law of conservation of energy, which is not possible. Output is having its own limitations. It cannot go beyond certain values, whatever may be your input. Okay, please keep this point in mind. And the ideal op-amp equivalent circuit is like this. So then, what is the advantage of this ideal values or characteristics of ideal op-amp? Let me take from that the significance of each value we will see, which is well known to all of us, of course. See, the characteristics of ideal op-amp: infinite input impedance, that is Ri is infinite, and zero output resistance, Ro is equal to 0. Infinite bandwidth, see, it's an electronic circuit, a system, it has its own bandwidth. So ideal value, no, ideal person, anything we can write. Anyway, ideal device, we are writing high input impedance, practically very large, ideally infinity, and zero output resistance, ideally, right, practically 10 to 100 ohms, practically it is ideally 0. Okay, bandwidth and infinite voltage gain, A is tending towards infinite. Okay, so these are the values we can write, ideal values. Then what is the advantage of infinite input impedance, or what is the advantage of each of these parameters? Let us see. Significance of high input impedance, anyway well known to all of us. So here, if you consider a voltage amplifier, we have already studied earlier also. First, let us start with a voltage amplifier. Later we can go to this operational amplifier, VS, RS, and it has some load resistor. If you take this, there is a current flow in the device. What is the current, input current, I can say? II. It is Vs by Rs plus Ri. Okay. And what about input voltage? Voltage division rule. That is Vs into Ri by Rs plus Ri. Okay. Similarly, output side, if you take V output, I am using voltage division rule and writing it A into Vi by Ro plus Rl multiplied with Rl. This is well known to us and we discussed it earlier in the previous sections as well. Okay. So while designing this amplifier, okay, while designing the amplifier, what we are looking at, If Ri is very much large, if I design my amplifier with high impedance compared to Rs, then Ri plus Rs is approximately equal to Ri. So that Vi is equal to Vs into Ri by Ri. It is Vs. The first point means my amplifier absorbs as much signal as possible from the source, independent of the source resistance. I need not worry about the source resistance. Okay. Similarly, coming to the output side, suppose my amplifier's resistance, output resistance is very much less compared to RL, then RO plus RL is approximately equal to RL. So that V output is equal to A into Vi by RL multiplied with RL. RL cancel. It is A into Vi, which is equal to A into Vs. Means my output has become independent of RL. Okay. So I have designed amplifier and I gave it to you. I asked you to connect whatever the source you want to connect, you can connect. And I told you to connect the load whatever you want, you can. I need not bother about the performance of my amplifier. That's it. Right? The source resistance may be 1 ohm or 10 ohms or 100 ohms, 1K, doesn't matter. Always Vi is equal to Vs. Okay, you want to test me, so you may connect a source. Source may be like a 2 volts source, but your internal resistance may be 10 ohms or 50 ohms or 100 ohms or 1K. If source resistance changes according to this equation, Vi keeps on changing. But if I design my amplifier with extremely high value of Ri, I need not worry about the source resistance. Similarly, output voltage is looking like it is dependent on the load resistance. To test the performance of my amplifier, you may connect a load resistor of 10 ohm or 100 ohm, 1K, 1 mega. And if the load resistor changes, the output value keeps on changing. But as a designer, if I take care of my output resistance, if I design the amplifier with very low value of RO, then V output is independent of RL. That's what is very much required. I should not say that you have to connect a load of so and so. As a designer, I should challenge you. You connect any load of your choice or you connect any source of your choice. My amplifier will give the best performance. That is the idea. So Ri should be high and RO should be low. Anyway, gain should be high to convert even small signal into large signal. That is fine. So as Ri is very much large, ideal value of Ri, what you can write? Infinity. And ideal value of RO is 0. So if I take ideal voltage amplifier, what happens here? Ri is infinity and RO is equal to 0. If that is the case, this is the equivalent circuit of ideal voltage amplifier. Then what about Vi? Is there any current that is possible here? No current enters into the device. Means my voltage amplifier is not loading the source, I can say. Okay, and always Vi is equal to Vs. So amplifier is not loading the source. Due to infinite input impedance, no current enters into the input terminal of amplifier, so that it does not load the source. Similarly, coming to output side, due to zero output resistance, right? Here Vi is always equal to Vs. And due to zero output resistance, V output is equal to RL. See, depending upon RL, IL value will change, but V naught does not change. Okay. So, as the first point here is like this, amplifier does not load the source, or the current entering into the input terminal of the amplifier is 0. So, there is no voltage drop across RS, and enter Vs can be seen across the input terminals. So, amplifier is not loading the source, right? And as RO is 0, V output is always equal to, second point is, V output is always equal to A into Vi. Anyway, Vi is equal to Vs. We can write like this. So, this is the idea of an ideal voltage amplifier. That's what you can take even for operational amplifier. Ideal op amp has infinite input impedance and zero output impedance, and hence what happens? Okay. Now, you take ideal op amp. V output. Okay, or you can even take with practical op amp also, doesn't matter. Okay, from that also we can take it. Anyway, if I take this one, so inverting and non-inverting terminal, op amp has the power supplies VCC minus VCC like this, and here it is V minus and it is V plus VD. So ideally input impedance is infinite. Due to infinite input impedance, the current entering into any of the input terminals is always 0. Is there any current that is possible? I minus, it is 0. And is there any current that is possible in this direction? No. I plus is also 0. So due to infinite input impedance, the current entering into any of the input terminals is 0. And hence the op amp never loads the source, okay, which absorbs the maximum possible voltage from the source. That is the idea here. So as Ri is infinite, what is the significance of high infinite input impedance? Means as Ri is infinite, the current entering into any of the input terminals, or both the input terminals, I can write current entering into both the input terminals, is always 0. Okay, is 0 I am writing. So that op amp never loads the source, and the op amp hence it's much better way of writing. Never loads the source. This is very, very important point. Input impedance, differential input resistance is infinite. So practically very large, ideally infinite. So it does not allow any current to enter it, which means it is not loading the source. If it loads, right, if some current flows, it starts loading the previous stage. That is the significance of, right, or advantage of the high input impedance. Okay, just voltage amplifier, if you know, the same thing I am extending here. to the op amp, nothing else. And coming to the significance of low output resistance, ideally 0. Okay, see the op amp, if you take so practical op amp, some load resistor is connected RL. Then what is V output? As usual, A into Vd multiplied with RL, or V output is equal to A into Vd multiplied with RL by RO plus RL, because this is how the current is flowing. Well known equation. Now if RO is 0, what happens in ideal op amp? So output is dependent on RL. V output depends on RL. In practical op amp. Whereas in ideal op amp, you connect the load resistor RL, V output. So it is always equal to V output is equal to A into Vd. Is it dependent on the load resistor? No. IL. Depending upon RL, IL may vary, but output does not change. Always. V output is equal to A into Vd, or A into V plus minus V minus, which is independent of, right, RL. So V output is independent of RL. So due to infinite impedance, it is not, op amp is not loading the source. That is the significance or advantage of infinite input impedance. Okay, and what is the advantage of low output impedance? Means output voltage is independent of RL. Whatever the load you connect, doesn't matter. Okay, next point, significance of large bandwidth. Bandwidth is high, means the first advantage is we can operate op amp over a wide range of frequencies starting from DC. The advantage with op amp is you can even amplify the DC signal. So the advantage is due to large bandwidth, op amp can amplify, or op amp can operate on signals, or op amp responds to the signals from DC to high frequency. That is the advantage. And second point is, we know the rise time TR of a system is given by 0.35 by bandwidth. Of course, the bandwidth in hertz, otherwise 2.2 by bandwidth in radian per second. So it is inversely proportional. Bandwidth is more, rise time will be less, which means as the bandwidth is large, the response is fast. Due to large bandwidth, response is fast. This is the significance of large bandwidth of operational amplifier. Okay. The next one, infinite gain. What will you do with infinite gain? Okay, need to see that. Anyway, if you take ideal op amp, we can take all these statements. Ideal person, we can write some statements. What are the advantages of ideal person? We can write in a similar fashion. We can write the advantages of ideal operational amplifier. To be frank, ideal person is useless. Okay, similarly, ideal device is useless. We can think of approaching towards ideality. We should not reach that point of ideality. That is a big loss. Okay. Anyway, let us not discuss much. It's not live section recorded. No. So, significance of large gain. For understanding that, let us start with an op amp with a gain of some 10 power 4 and conclude what happens if that gain is infinity instead of some 10 power 4. Okay. So, let me take an op amp V minus V plus with power supplies of 15 volts and minus 15 volts. Consider an op amp with gain A is equal to 10 power 4. Okay. Then V output is equal to A into Vd, where Vd is nothing but V plus minus V minus. So many times I wrote it, it is Vd. Taking it from non-inverting terminal to inverting terminal. This is what I am writing for Vd. Okay, that's the notation we follow. Right. So what I am doing is, let us apply some input to the inverting terminal and connect. Let us give some input to the non-inverting terminal and connect the inverting terminal to 0. It is connected to ground. I am giving here some 1 millivolt input. Then what about V output? It is a 10 power 4 into Vi. I can write A is 10 power 4. So if V input is equal to 1 millivolt, what is the output? 10 power 4 into 10 power minus 3, 10 volts. Excellent result. From 1 millivolt, you are producing 10 volts. And suppose my input is 1.5 millivolt, the corresponding output is 10 power 4 into 1.5 into 10 power minus 3. It is 15 volts. Excellent. Whereas if my input is equal to 1.6 millivolt, what is the corresponding output? Gain 10 power 4 into 1.6 into 10 power minus 3, 16 volts. Is it possible? No. The output should never exceed the power supplies. So, not possible. So, what is possible? Output can reach a maximum of 15 volts. This value is known as V saturation. That is V output maximum. Ideal value of the saturation level. It can't go beyond it. You may apply 1.7 millivolt or 1.8 millivolt or 2 millivolt, 5 millivolt, etc. The output can reach a maximum of power supply plus 15 volts. That is the first point. Next, similarly, if I give some negative input, suppose my input is minus 1 millivolt, what is the corresponding output? 10 power 4 into 10 power minus 3 minus 10 volts. And suppose my input is minus 1.5 millivolt, the corresponding output is directly I'm writing it is minus 15 volts. And if it is minus 1.6 millivolt, the corresponding output is minus 16 volts. Not possible. It is exceeding the power supply. So what is V output possible value? It is minus 15 volts. It is known as minus V saturation. It is also known as V output. Output cannot go beyond minus VEE. That's it. So output maximum and output minimum are like this. If you apply input to the non-inverting terminal. In a similar fashion, we can apply input to the inverting terminal also. So later, if you give minus 1.7, minus 1.8, minus 2, minus 5 millivolt, etc., the output cannot go below minus 15 volts. It got saturated. Okay. Similarly, let us consider the second case, like apply input at the non-inverting terminal, plus 15, minus 15, V output, connect the non-inverting terminal to ground. Output is equal to A into V plus minus V plus is 0. It is minus A into A. Okay. Suppose my input is equal to 1 millivolt, the corresponding output minus 10 power 4 into 10 power minus 3 minus 10. Yes, input is positive, the corresponding output is negative. We are applying signal to inverting terminal. So next 1.5 millivolt, the corresponding output is minus 15 volts. If I apply plus 1.6 millivolt, what is the output? Minus 16 volts is expected, which is not possible. What is the possible value of output? It is minus 15. This is known as minus V saturation, or also I can call it as V output minimum. Okay. And similarly, later you apply anything, 1.7, 1.8 millivolts, 2 millivolts, 3 millivolts, the output cannot fall below minus V saturation or minus 15. Similarly, if my input is minus 1 millivolt, the corresponding output is minus 10 volt. It is minus 1.5 millivolt, the corresponding output is plus no, negative input, output should be positive. And my input is minus 1.6 millivolts, the expected output is 16 volts. It is not possible. So what is possible? It is V output maximum. It is equal to plus 15 volts. It is known as V saturation. That's it. And later you may give minus 1.7, minus 2 millivolt, etc. The response cannot go beyond plus 15 volts. That is the property of operational amplifier. Okay. Based on this, I would like to draw the transfer characteristics of the operational amplifier. Okay. And here I showed one more point. I applied input either at non-inverting or inverting terminal. Right. Okay. One non-inverting terminal, positive and negative inputs I gave and I wrote it. Similarly, I applied input at the inverting terminal I showed. Right. Instead of that, what I can write is VD, that is the differential input, which is equal to V plus minus V minus VD is equal to V output by A. I can write it. And VD maximum, the differential input maximum, it is equal to V output maximum by A. What is V output maximum here? Plus 15 by A is 10 power 4, that is 1.5 millivolt. The differential input means V plus minus V minus, the maximum value of the difference is 1.5 millivolt. If it is more than that, the output cannot go beyond 15 volts. Similarly, VD minimum is equal to output minimum by A, that is negative power supply. It is minus 15 by 10 power 4, 1.5 millivolt. Means as long as your VD is within this range, your output, you can use the equation. I can write here, as long as minus 1.5 millivolt less than VD less than 1.5 millivolt, I can use the equation V output is equal to A is equal to VD. Otherwise, you cannot use this equation. Out of this range, you can't use this equation. Okay, please do observe this. That is dependent on the range of input. VD depends upon your gain A and the power supplies you are connecting to the operational amplifier. Based on that, in this example, I am writing it. So now consider the transfer characteristics of op-amp. I am writing it like this. Transfer characteristics means it's a graph drawn between output and input. V output to VD. And V saturation, how much it is? Plus 15 volts. And minus V saturation, it is minus 15 volts. And how long you use this equation? Slope is equal to A. So because V output is equal to A into VD, I can write it. So it is like the straight line. A is into VD means it is similar to Y is equal to mx. What is the slope here? Slope m is equal to A, or I can write slope m is equal to tan theta, it is equal to A. Okay, so see this slope A whose value is 10 power 4 in this example. And how long we can use this equation? This is the maximum value of input, it is 1.5 millivolt, it is 0, and minimum value of input is minus 1.5 millivolt. Within this range, we can use this equation. Output is equal to A into VD. Okay. And what about this angle theta? If you take so, right? A, it is tan theta. We are well aware. Then, okay, tan theta is equal to 10 power 4 implies theta is equal to tan inverse 10 power 4. Its value is found to be 89.99 degrees, almost 90 degrees. Just I showed here like this. But the thing is, if you look at this angle, it's almost like 90 degrees. It's almost like a vertical line. Okay. Just for our understanding purpose, I wrote the range of input is like this. As long as input is in between minus 1.5 to plus 1.5, we can write the equation V output is equal to A into VD. And output maximum is 15 and output minimum is minus 15. If input is greater than 1.5 millivolt, output is plus 15. Input is less than minus 1.5 millivolt, output is minus 15. Everything is fine. In which the theta value, if you calculate, so it is coming to be 89.99 degrees, means it is almost like a vertical line. But here I showed it like some 45 degrees angle. Slope is 1 like that. But it is extremely high. And here if you see 1.5 millivolt means if you observe the value, it's very much close to 0 only. It is nothing but 0.015 volt. Is it not close to 0? And minus 15 millivolt means it is equal to minus 0.015 volt. It is also very close to 0. Okay. The reality is, even though I am showing it like this, the reality is this is how the transfer characteristics appear. VD, V output. Anyway, this is V saturation plus 15 volts and 0. It is minus 15 volts. Almost like vertical line. 89.99 degrees. You see. And the second thing. Suppose the gain is 10 power 5 instead of 10 power 4. Then what we get? Here, if A is equal to 10 power 4, this is the range of your input. Suppose A is equal to 10 power 5, then what is the range? One more 0 will be added. It is minus 0.0015 volts to it is 0.0015 and A is 10 power 6. It comes much close now. Okay. Is it not so? Sorry, 1.5 millivolt, no? That's correct. Like this. So as the gain increases, the range of input comes down. Almost it approaches. So what is the slope? If it is A is equal to 10 power 5, means theta will be equal to 89.9999, something like that. It's almost close to 90 degrees. Or the range of input. Here I mentioned the range of input, previous slide. The slope, right? Slope is right. The range of input compared to this second, if it is 10 power 5, the range will much decrease. 10 power 6, much decrease in the range of input. If it is infinity, right? What we can write? If A is equal to infinity, ideal op amp. In ideal op amp, in case of an ideal op amp, A is infinity. That is the slope m or tan theta is equal to infinity. Implies theta is equal to tan inverse infinity. It is perfectly 90 degrees. Perfectly 90 degrees means it is a vertical line. The transfer characteristics, how do they appear? Instead of the slope, you can see a perfect vertical line. Transfer characteristics of ideal op amp. Here it is perfectly 90 degrees. A is infinity slope. Slope of a vertical line. It is plus 15 volts and it is minus 15 volts. So from these characteristics, what we can write, if A is approaching infinity, then what we can write? See, if VD is positive, output is Vsat. And VD is negative. If VD is negative, output is minus Vsat. That's it. Okay. So what we can write here, if VD is positive means greater than 0. VD means V plus minus V minus greater than 0, or V plus is greater than V minus, all mean the same. Our output is equal to V saturation. That's it. Similarly, from this what we can write, if VD is less than 0 or V plus minus V minus less than 0 or V plus is less than V minus, what is the output? It is minus V saturation. Means if you take the op amp in open loop configuration, take inverting and non-inverting terminals V plus and V minus. Generally I am writing 15 and minus 15, but they need not be. So if A is approaching infinity, what we can write? If A is approaching infinity due to large gain, instead of differential amplifier, op amp behaves like a comparator. It is just comparing the voltages here and here. If voltage here is, or voltage at the inverting terminal is, non-inverting is dominating, positive input terminal is dominating, output is plus V saturation. And if voltage at the inverting terminal or inverting input terminal is dominating, output will be minus V saturation. Means instead of a differential amplifier, op amp behaves like a comparator. That's it. That's the point we can write. So if A is approaching infinity, then op amp in open loop configuration, I'm not applying any feedback. open loop configuration. In open loop configuration, behaves like a comparator instead of differential amplifier. This is the idea. Okay, then how can we use the op amp as an amplifier? Ideal op amp I'm speaking, gain is infinity I'm saying, and simply what it gives, as the gain is infinity, it cannot give infinite output. What it is giving? It is giving either V saturation or minus V saturation. That's it. Then how can I mentioned like op amp can be used as, okay, sorry, here I forgot to tell one more point. This slide I missed. Sorry. Why the name operational amplifier? Okay. So it is a high gain amplifier, it is fine. Along with amplification, what it is additionally doing, what operations it is performing, that's what you right, and you gave this name operational amplifier. Means besides amplification, op amp performs the arithmetic operations such as addition, subtraction, multiplication, division, and also mathematical operations like differentiation, integration, logarithmic, anti-logarithmic operation, and also the comparator. It also behaves like a comparator, just as I told. It is comparing the voltages at inverting and non-inverting terminals and gives the output, either positive or negative or zero, something like that. So comparison is also possible. That's why the name operational amplifier. Along with the regular amplification, it performs. Okay, this is also fine. And if the gain is infinity, you can see only the comparator application, but we are unable to see the remaining applications like addition, mathematical operations, or basic amplification. Okay, for that what we need to do means we need to apply negative feedback. We need to apply, it's an open loop system. So for this open loop system, we need to apply some feedback. By applying some feedback, we can reduce the gain. And we can reduce the gain means then you can operate the amplifier over a wide range. Right, and wide range, you can operate it over wide range, and that region is of course called linear region. In the linear region, you can able to write y is equal to mx. It is a linear graph. And non-linear, it is mentioned non-linear. The reason is the output is either plus V saturation or minus V saturation. Maybe 1.6 millivolt or 1.7, 1.8 or 2 millivolt, whatever may be the thing. It is simply either plus V sat or minus V sat. That is called non-linear region. Okay. So that's the meaning of these points. So by applying some feedback, I can reduce the gain. With a negative feedback, we can reduce the gain. We apply negative feedback and reduce the gain, and we can increase the non-linear region of op amp. Okay, how it is so, those things we will discuss in the next session.